Welcome students for the chemistry lecture. Here physical chemistry paper number 15, and last time you have studied the solid state chemistry, and in that lecture you have learned the what is crystal lattice, what is lattice sites, then what is unit cell, then the laws of symmetry, and in that you have learned the plane of symmetry, axis of symmetry, and center of symmetry. Today you are going to learn in detail the simple cubic system and the different types of simple cubic system. Okay, so here the crystal lattice, it is the geometric arrangement of lattice points in a crystal. Crystal lattice, it is the geometric arrangement of crystal. Okay, then a unit cell is the small box-like unit from which you can construct a crystal by stacking the units in a 3 dimensions. There are 7 basic shapes possible for unit cells, which give rise to 7 crystal systems used to classify the crystals. And this is the unit cell of copper. Here the 3-dimensional network of lattice sites. It is the crystal lattice or space lattice or simply crystal. Okay, and these are the lattice points. Okay, here lattice points, they are situated at the corners as well as at the center of this upper face. Here this is again next face. Okay, here this is a FCC crystal, that means face centered cubic lattice. Okay, the actual position of the lattice point, it is given by a lattice point or lattice site. Okay, the position of the points in the crystal lattice, it is shown by the lattice points. Then the unit cell shapes of different crystal system. Here in case of cubic, there is a 90-degree angle between two faces. In case of tetrahedral structure, here this angle alpha 90, beta 90, and gamma also 90. In this case cubic, alpha angle, beta angle, and gamma angle are also same. Okay, then here orthorhombic crystal structure, these angles are same one. Here B, it is equal to A side, and C, it is equal to A. Here A side, this is B side, and this one C side, and here B, it is equal to A, and C, it is equal to A. Okay, then monoclinic structure, this is, then hexagonal structure, then rhombohedral structure, and triclinic structure. These are the 7 crystal systems. Then see here the 7 crystal systems. They are cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, and triclinic. The specific characterization of the triclinic structure, in this case A, it is not equal to B, it is not equal to C. Okay, and alpha, it is not equal to beta, and it is not equal to 90 degree. Okay, then in case of rhombohedral structure, A side equal to B side equal to C side. Then in case of hexagonal structure, A equal to B, but B equal to not C. In case of monoclinic structure, A equal to, it is not equal to B, it is not equal to C. In case of rhombohedric structure also, A, it is not equal to B, it is not equal to C. Okay. In case of tetragonal, A is equal to B, but B is not equal to C. Only in case of cubic crystal, A it is equal to B, it is equal to C. Okay. And you have studied the law of constancy of interfacial angle. While any crystal structure is formed, the angle between the two faces it remains constant. Then you have studied the law of symmetry and the law of rational indices. Okay. Then here in case of simple cubic, there are again three types: a body centered cubic unit cell, face centered unit cell, and here a body centered cubic unit cell is one in which there is a lattice point in the center of the cell as well as at the corners. That means there are in all 9 points in the B.C.C. structure. B.C.C. means body centered cubic lattice. Then in case of face centered cubic lattice, unit cell is one in which there are lattice point at the corner of each face of the cell as well as at the corners. Okay. Here in case of FCC cubic unit cell, there are lattice points at the center of each face and as well as at the corner. That means cube has 6 faces, and at the center of each face there is a 1 point, and cube has 8 corners. That means 8 plus 6, there are in all 14 lattice points in the FCC structure. Here is a diagrammatically represented a simple cube. The characteristic of simple cube, here there are 8 points and they are situated at the 8 corners of the cube. Okay, here 1 point, second, third, fourth, sixth, and so on. The total number of points or lattice sides in the simple cube, here 8 points. Okay. Then in case of body centered cubic structure, in the center of the cube there is a 1 point, and the distance of each face from this central point, here it is equal distance. All these faces are at equal distance from this central point, and such structure it is the body centered cubic structure. And total points in the body centered cubic structure, here 8 points are at 8 corners and 1 point at the center of the cube. Therefore, total points in the BCC there are 9. And in case of FCC, at the center of each face there is a 1 point. And for cube there are 6 faces. So the 6 points they are situated at each face. Here 1, 2, 3 and 4. This one 5 and this one 6. So the 6 points they are situated at the each face of the cube, and 8 points they are at 8 corners of the cube. So in all 14 points are there in case of face centered cubic lattice. Okay, and in case of simple cubic lattice, there are in all 23 elements of symmetry, and that 23 elements of symmetry are distributed as here rectangular planes of symmetry. It has three rectangular planes of symmetry, then diagonal planes of symmetry 6, then fourfold axis of symmetry 3, threefold axis of symmetry 4, twofold axis of symmetry 6, and the center of symmetry 1. Here in this way we have 9 planes of symmetry, 13 axes of symmetry, and 1 center of symmetry, and the total sum of all these symmetry, it becomes equal to 23 elements of the symmetry. Remember well, in case of cubic crystal there are highest number of elements of symmetry, and for example the crystal of copper sulfate pentahydrate has no elements of symmetry. In case of copper sulfate pentahydrate, that means CuSO4 5H2O, there has no elements of symmetry. Okay, so you have studied the uh, simple cubic structure. Okay, simple cubic, body centered cubic, and face centered cubic. Then this is the cubic unit cells, simple cubic, body centered cubic, face centered cubic. These are the diagrammatically shown the points which are present in the simple cubic, body centered cubic, and face centered cubic. Here space filling representation of cubic unit cell. Okay, face space filling representation of cubic unit cell. So, the cubic crystal lattices are of three types. In case of simple cubic, the 8 points, they are situated at 8 corners. Therefore, the total number of points here 8 into 1 divided by 8 atom per corner. Okay, 8 into 1/8 atom per corner, and it is equal to 1 atom per cell. Remember, 1 atom per cell. There is a in case of simple cubic. Then in case of body centered cubic structure, here BCC, 8 points at 8 corner. Therefore 8 into 1/8 atoms per corner plus 1 atom in the center, and it is equal to 1 plus 1 2, 2 atoms per cell in case of BCC. Okay, then in case of FCC, here 8 points at 8 corner, therefore 8 into 1/8 atom per corner plus 1/2 atom per side, that means 1/2 atom per side into 6, and it is equal to 4. So 4 atoms per unit cell. Remember, in case of FCC, there are total 4 atoms per cell. 1/8 means 1 atom and half atom per side. Therefore, 6 sides, 6 divided by 2, it equal to 3. 3 plus 1 equal to 4. Therefore, in case of FCC, face centered cubic lattice, there are 4 atoms per unit cell. Then these are the inorganic crystal structures. Okay. Then so let us see the next point of your syllabus. The lattice planes and Miller indices and Wess indices. Here, lattice plane is any plane containing at least three non-collinear lattice points. These are the primitive cubic lattice planes. This plane is a 100 plane. And you know 100 plane, that means it plane cuts only one axis, and that plane it remains parallel to the another two axes. Then in case of here 100 plane, that plane cuts two axes and it remains parallel to the third axis. While this plane 100 plane, it intersects at the three coordinate axis. Such plane it is called as 111 plane. These are the face-centered cubic planes. This is 200 plane, 220 plane, 1110 plane. Okay. Then lattice planes and Miller indices. The orientation of a surface or a crystal plane may be defined by considering how any plane intersects the main crystallographic axis of the solid. The application of a set of rules leads to assignment of a Miller indices, and in general the Miller indices they are represented as H, K, L. These are a set of numbers that may be used to identify the plane or surface. To calculate Miller indices, follow the following steps. Determine the intercepts of the face along the crystallographic axis. And remember, the intercept made by the face or plane along the crystallographic axis, it is it is the Wess indices of that plane. Okay, that is called as Wess indices of that plane. Then the reciprocal of Wess indices, it is called as Miller indices. Then to calculate the Miller indices, at first you must know the intercept of the face along the crystallographic axis. Then take the reciprocals, then clear the fractions and reduce to the lowest term. And Miller indices, they are usually represented in a smallest number and in whole number and not the fraction. Here, for example, if x, y and z intercepts are 3, 1 and 6. Suppose a plane is there, it intercepts on x-axis, y-axis and z-axis, and that intercepts are 3, 1 and 6. Then the Miller indices are calculated as follows. The reciprocals of here, on x-axis it is 1 by 3, on y-axis it is 1 by 1 and on z-axis that is 1 by 6. Then clear fractions, that is multiplying by 6. Here we get 2, 6 and 1. Here multiplying by 6 we get 2, 6 and 1. Then reduce to the lowest term. Then the lattice planes and Miller indices. Here, the following treatment of procedure used to assign the Miller indices is simplified one. Only cubic crystal system having a unit cube with dimensions A into A into A will be considered. That means A, it is equal to this A into A. And this is a, a 100 plane. Here the side of this cube, here it is 1 unit cube. If we consider, here they have considered A side, therefore this is a A00 plane, and its intercepts are A infinity infinity. Okay, then the next point here you have to learn, and that are the Bragg's equation. Okay, how the Bragg's equation is used to determine the crystal structure, we will see later on.